Okay, we'll be having a short recap of graph theory, the async material that I uploaded previously, and siguro, if we have time to get into DFS and BFS and other graph properties that we'll be using throughout this course now. At any time in this sync session, if my screen stops sharing because I'll be switching devices fairly often here, let me know. I might not be able to see it, so just either make a sound, raise your hand, or react. Just bring attention na lang. Okay. As always, if there are any questions from the previous material or from the material we'll be using now, just let me know. Sige. Give me a bit to share my screen. Midterm specs are out na pala, so just make sure to check Canvas for that. Where is it? Okay. So let's get into it really quickly. Just to quickly recap, no. Um, yeah. So this is, sorry. Ito. An intro to graph theory. Just a quick recap for those who might not be too familiar with the material. No? So, graph theory is the study of networks of graphs, which are mathematical structures used to model pairwise relationships between objects. No? Graph in this context is made up of vertices or nodes, which are connected by edges or links. No? So, normally we use lists to represent sequential data, or array lists, or even arrays. We use we use graphs or networks to model relationships between objects, no? And that's why the social network, the idea of the social graph, is really a profound and strong one, because we're able to model relationships between people, and put value to them, assign value to them, no? And this is way more efficient than doing other data structures to represent relational information like this. So here is a social network. It's a visualization of a Twitter mentioned network, and here we have nodes, vertices, essentially, that are colored, no, and they're white lines that traverse the graph, like connect the nodes to each other, are instances when people mention or have mentioned each other. So this is a demonstration of that. This is the London Underground. Um, if you guys watch the Euro, this place is probably super trashy right now because of what happened with the English team. But essentially, it's a network now. So we don't only use networks or graphs to represent uh, data structures in computing. Now, we also use networks and graphs to represent information visually that have some sort of path to them, that have a sort of sequentiality in a network. And what does that mean? So here we have the various nodes, the various dots in this visualization. And these are essentially the stations in the London Underground. No? Here we have the colored lines, and each line represents a specific path. And these lines are basically connections between the stations to each other. No? And you can see that there are transfers here where the lines intersect. There are lines that traverse the network in one direction and another one through another direction. There are lines that traverse, for example, a subset of the network, and there are lines that traverse almost every point. No, so if you guys have played, I don't know, City Skylines, or I don't know, Civilization, and you're building your road network or your transport network, you probably have encountered this. No, where there are routes that are more cyclic. There are routes that take, for example, traverse every point. But then there are also routes, there are also paths that only traverse a subset of the points. And this is very critical in graph theory. There are more efficient ways to go from point A to point B rather than taking the whole walk through the whole graph. And we'll get into what that means, why it's termed a walk. So it's usually called, walking the graph or doing a random walk. Is basically, it comes from the whole idea of the seven bridges of Königsberg when Leonhard Euler in 1736 essentially founded graph theory. The challenge was take a walk through Königsberg by crossing all of the bridges just once. And there are seven bridges in the city. So this is not possible. Um, but this is what essentially laid the foundation, um, the study of graph theory, of topology, of pathfinding. And we all know about the traveling salesman problem. It's very similar, no? How do you optimize a path without repeating anything? So graph theory is very important, not just for AI, for pathfinding, but also for navigation, for visualization, for representing tools that are representing information, that have a more relational aspect to them. Instead of displaying something in a tabular manner, why not just display it as a network? So here we have a flowchart, another very common use of a network. This is a directed acyclic graph. When I say directed acyclic graph, it means its edges have direction. You can't go back from baking a pizza here in the end and then apply tomato sauce. That's weird. There's a sequentiality to how you traverse the graph now, and that's why it's called a directed graph. Acyclic means acyc. What's the good? Acyclic basically means that there are no cycles, no. So the prefix a and cycle basically tells you that there cannot be any cycles in this graph. So a directed acyclic graph is what's commonly used for a lot of flow charts, programming flows. If you guys have worked with Apache Airflow, it uses a DAG, directed acyclic graph, to chain machine learning models in sequence. If you write code, if you guys are familiar with Scratch, the programming intro to programming tool, you also use a DAG for most of those things. And so graphs and these other tools are very useful in representing information. One of the cool things is that in video games, many, specifically in RPGs, no, many um, concepts in RPG lore are based on graphs. You have your skill tree, you have your character tree. In Civ, you have your tech tree, your culture tree, your, I don't know, and it represents some sort of sequence by which you unlock specific skills. And then once you unlock a skill A, you then branch out into these other sub skills or subspecialties. So you can think about it as, for example, taking your various CS, MIS courses or even grad courses. You come in first year, generalize, and then as you get enough, siguro, how do I say this? XP points, you're able to put these XP points into your specializations. Oh, I want to take the DS AI spec. Oh, I want to get into the game development spec. I want to get into the ES spec. And as you go along, there are definitely prerequisites. If you want to take the AI spec, the DS spec, you can't jump into like um, machine learning without knowing an intro to programming. You can't go into data visualization if you haven't taken machine learning, because what is there to visualize, no? So there's some sort of sequentiality to it, and trees and graphs are usually the best ways to represent these things. So do take note that trees are nothing more than just restricted kinds of graphs. A tree will always be a graph, but not all graphs are trees. So just keep in mind. Okay. So some notation, this is the formal definition of what a graph is. A graph G is a non-empty finite set of vertices V along with a set of edges E, which are essentially tuple subsets of V. So let's get into a better definition of that. So let's start a new one because that was from earlier. Let me know if there are any questions, clarifications. Sige. Okay. So let's play with this here. Oops. Okay, so we have here a graph G with vertices V and edges E. Okay, so normally it's noted as GVE. Okay, where you have V, which is your set of vertices, so it's some set, and E, which is some set of edges. Okay, so let's get into this. So let's define this graph. Let's call this G sub 1 here. And then let's have here a node A, a node B, a node C, node D, and a node E. Okay, so this is a directed graph. And if you guys are familiar with this is essentially a binary tree. This is a binary tree where you have two children spawning from a single parent. So let's list the edges here. So G1 is equal to, let's say, V sub 1 and E sub 1, where V sub 1 is equal to A, B, C, D, and E. And E sub 1 is essentially, so this is a directed graph. And when you identify edges for a directed graph, now the sequence by which the edge flows matters. So I have to care about the order. So I here have edge AB. Sorry, that's not clear. I have here edge AC. I have edge BD. And I have here edge BE. Okay? Sorry, that's horrible. Okay, so when it's a directed graph, order of when you identify the edges matters. So if I put something like edge BA here, for example, edge BA, that would be wrong. No, I need to call it edge AB because there's sequentiality to this directed graph. Okay. So any questions or clarifications, guys? You guys okay? Good. Sige. Okay, let's go back to it. We'll now talk about weighted graphs, specifically weighted edges. No? There are nodes, there are networks with weighted nodes, weighted vertices. We'll go into that later. But we'll talk about weighted edges first. Okay. So let's say we have a directed graph. No, directed graphs are usually the more interesting ones, but definitely undirected ones have value. Okay. So let's say I have here the start node. Let's go with brown. The start node. And I have here the second node. And I have here this other node. And then they all end up at some node here. Okay. Okay, so then let's then take this analogy, let's scale this to something more interesting. Let's say this is the Civ 6 or Civ whatever skill tree. Okay. So, how do I let me pause my share so I can give you guys some better context. Okay. Um Here we go. Okay, in the video game Civ, so it's if you and if none of you guys are familiar now, so Civ. Sorry, why am I clicking? Civ is this video game where you try to take your civilization. You start out in maybe the Stone Age or in whatever age you prefer, usually the Stone Age or the prehistorical ages. And you try to level up your civilization throughout history by researching technology, conquering opposing nations with that sort of technology that you want. No? So this is what it typically looks like, where in this case, no, you have to unlock advanced flight, rocketry, ballistics. You have to unlock plastics before you get into synthetic materials. You have to unlock flight, rocketry, advanced ballistics, and combined arms before you get to nuclear fission. Others, you'd have to, um, yeah, essentially sort of the same thing. Going earlier, you have to progress through specific ideas or phenomena like apprenticeship and stirrups before you get to education. You have to unlock machinery to get crossbows or that sort of thing. So that's Civ. And let's pretend that we are there and we have here this skill tree, no? Here. And so let's say we are here at the Stone Age. Let's say this here is the Stone Age. And then this one here is, I don't know, maybe when writing was developed here. Here, let's say painting was developed. And then we progress through time. We develop painting, we develop machines. I don't know, this is not the best analogy, maybe. We develop machines, we develop um, mass production, we develop computers, and then we develop the space age. We get to the space age. So, this is the goal. This is essentially our goal state. Sorry. And then here, for example, we have this other tree where we just push writing so much that we develop some old, arcane, crazy, weird, I don't know, Turing machine. Because technically we can compute using machines. So what if history took a different route? We did not discover transistors. We just took writing, developed machinery out of that to build computers, and through a buttload of Turing machines, we get to the space age now. So let's say this is how history progresses. Absolutely does not make sense, but let's go with it for the sake of this analogy. And let's say that there are weights to the edges. How long does it take for us to develop these technologies? Let's say for painting from the Stone Age, it gives us, let's say, I don't know, in hundreds of years maybe. So this is 1 year. From painting to machines, we get 3 years. Sorry, let's give the edges a different color. So this is 1, this is 3, this is 15, this is 5, and this is 2. Okay. And now from Stone Age to writing, maybe let's say we got something like 2. Sorry, let's go for like 5 years. And then let's give this like, I don't know, 30 years. 30 1,000 years or something. And then here from Turing machine space, that's 15. Okay. So this is the concept of a weighted graph, where you have nodes that are adjacent to each other, that are connected to each other by edges that have specific weights to them. What weights can mean? They could be values of time, they could be duration, they could be cost. Cost is something we'll be looking into, not just monetary cost, no, but essentially as a cost function. We could be looking at edges as a function of how hard is it to get to the next edge. So if you want to visualize ways as a graph algorithm now, you have here your locations. These could be your key locations along a route, and then you have ways connecting these routes through the road networks, through the roads, and through those roads you'd have edges now. So what these edges can mean is, let's go into a demo here. Sorry, Waze live map. Yeah. Okay, so you somewhat know where I live now. Let's go here. Okay, say I am in Ateneo here, somewhere here. Ateneo should be somewhere here. I don't know how to put a pointer right now, but say somewhere here in Ateneo, and I want to get to, let's say Quezon Memorial Circle. No, if I want to get to QC Circle from Ateneo, I can take CP Garcia, uh, or I can go through Saviorville, Camias, EDSA, and then what looks like, what is this? East Avenue. There are many ways to go about this. Think about this as, sorry, I think my screen was paused. Yeah, sorry, here. Ayan. Thanks. Yeah, I don't know why it keeps pausing. Yeah, if you can see this, yeah, pretend I'm here in Ateneo and I want to get to QC Circle. You'll see that there are multiple roads connecting Ateneo to QC Circle now. Think of these as edges along a network, and these edges will have various weights depending on traffic, depending on whether it's a one-way road, depending on whether there are obstacles, whether the road is crappy. That could be added cost to your vehicle, to your travel time. So it's not just purely travel time. You also have to take into account if you have, let's say, a UP sticker and you can cut through UP. You have to take into account those other variables. So edges can denote so many other things, not just time or cost, but a variety of other features. No? So think about this in your problem set. If you're trying to create a game world, what would your search space be? What would your problem be? What would your environment be? And how would you translate your states? No? What would your next positions be like? Okay. So let me go back. Tuning. Okay. Sige. Okay, now we can also have networks where nodes have specific properties. Let's go with green here. Okay, so here I have this graph. Let's call this my start state, and let's call this other one my end state. Okay, so this is start, this is goal, start and goal states, no? And then between my start and goal states, I will have nodes with weights and edges to them. Sorry, nodes and vertices with weights to them. Okay, so let's say here, um, let's call this node A, node B, node C, node D, and node E. Okay, so let's assign specific weights to them now. So this could be 1, this could be 2, this could be 2 again. Let's call this 1, this could be 3, this could be 2, this could be 1, this could be 1, this could be 5. Okay. And then we can assign weights now to our various nodes. No? So let's choose a nice color for this here. So for A, let's say we have a weight of 2. For B, we have a weight of 2 again. For C, let's have a weight of 1. Here we have a weight of 1. Here we have a weight of 2. Okay. Okay, so when we want to get from, sorry, when you want to get from S to our goal state, G, we want to consider the most efficient path, no? Be it in terms of cost. So we see here that there are 1, 2, 3, 4 paths. So this is, we have here path 1, path 2, path 3, and path 4. Okay. So let's define these paths. So for S to A to B to G, we have S to A to C to G, and then we have S to D to E to G, and then we have S to G. Okay, so we compute now for the various weights that are associated with these specific paths. No? So for, we can call this, sorry, we can put notation here. We can call this F, sorry. Oops. We can essentially call this F of A of B to get to G. And this could be F of A of C. This could be F of D of E. And this is just be F of G, just straight up. Okay. So computing, this is 1 plus 2 plus 2 plus 2 plus 2. So 3, what's this? 3, 5, 7, and 9. So this other one, ACG, is 1, 2, 3, 4, 5, 6, 7, 8. SDE is 2 plus 1, 3, 4, 5, 6, 7. And this other one, this other path is just 5. Okay, sorry. Okay, so these are things that you want to consider when identifying your shortest path. Now, sometimes if I want to get from, let's say, my house to Makati, Makati is pretty far. So I want to make sure that I live in somewhere in Antipolo. So when I go to Makati, I want to make sure that that trip is pretty much valuable. So I'll try to do errands on the way there. No? So if I'm telling my friends, okay, I'm meeting you in Makati at like, what is it now? 4. If I'm meeting you guys at Makati at like, sigating 8, I want to make sure that a trip from my house to Makati doesn't take 4 hours, no. But if I have stopovers in the middle, I want to make sure that I do stuff. I have to take into account the time that these stopovers will take. And so these could be nodes that are representative of that. No? So there are edges that denote travel time. There are nodes that denote stopovers or checkpoints or um, pit stops that can also have some time value to them. So you want to consider these things when doing route planning things. When you're doing agent-based AIs, you not only want to consider the cost of getting to your target objective, but how long you also stay there, what that means for your agent. No, there's also a cost associated with that. Sometimes there are cases with agent-based systems now that let's change the analogy here, where okay, let's go green. there is a node here, no? And then there's a node here. So let's say this is target node, um, sorry, let's call this EF. Okay, and we know that this edge has like a cost of, for example, 100. So off the bat, you see you're at node S and you see these three costs, no, 1, 2, and 100. You're like, okay, why would I go for 100? But it turns out 100 is like there's a wormhole there or something, or um, there's a cost of 100, but inside the node is something like negative 99. It's essentially a shortcut, maybe warping time or something like that. And this cost here is just maybe 1. No, so there can be those cases where your node essentially transforms the total cost that you're going drastically, and you don't know that yet. If I'm starting out here at S, I don't know that F has a negative 99. I know that 1, 2 are probably better options than something like 100. So I'll probably go with these two, not knowing that this will, in the end, save me much more time. So you have to take into account these sort of things when designing an agent based AI, that there can be functions, that there can be environments that might not be immediately obvious. When you get into machine learning later on, these are going to be called your local or your hidden minima or maxima states. And finding whether these exist and whether they're actually beneficial to your AI, to your model, is something that we'll be discussing, not in this course, no, but in the pattern recognition AI course. Okay, we've tackled weighted graphs, weighted edges, and weighted nodes. Next thing we'll be doing is discussing graph traversal, very basic graph traversal. Okay. See, any questions, guys? Wala naman. Sige. So when working with graph data structures, no, normally, if you guys are familiar with computational complexity, graph traversals are noted. The notation follow their vertex or their edges or some function of these. Now it really depends. So this is big O notation. Um, if I'm traversing a list, normally that would be an O of n, big O of n, because I will take as many steps as there are list elements now if I'm traversing a list. For graph traversal, I will take as many steps as there are vertices and edges now if I'm traversing the full thing. So it's proportional to O of V plus E. So think about these things. We won't get into the proof of these things so much. I understand that there are some students in this course who did not take programming subjects yet, no, but we want to think about um, sort of complexity estimates as well when we study graphs. And that's why it's very important to study really efficient graph traversal methods. And we'll be discussing two right now, breadth first search and depth first search. Depth first search. So the first one, depth first bleh, search or DFS. Do take note that it's depth first search, not depth first search. I've encountered that so many times from people all over the place. Yeah, please don't make that same mistake. Yeah, so DFS is a searching algorithm or a traversal algorithm. Now it can be depth, it can be depth first traversal or depth first search. In this case, we'll consider it as a searching algorithm. What it means is we essentially try to traverse a graph by expanding nodes that are more deep than there are wide. So let's go into what that looks like. Okay, so DFS. Let's start here with some nodes here. Okay, follows. Okay. So when what DFS does is we find, for example, a start node here. Let's call this, sorry, our start node. And what DFS does is it tries to expand nodes um, as far as it can go. So let's work with a quick, really quick demonstration. I'll mark nodes yellow for, is that a brighter one? I'll mark nodes yellow for nodes that we visited already. Okay. And that nodes that we're expanding. Okay, so I start at node S. I know that node S has 3 children here. I look into either of them, no? Let's say I start with this one on the left, just for kicks. It can be random, whichever immediate children we have. Okay, here. Okay, so this node here has 2 children. Let's say I go with the one on the left again. Okay, so this node here still has a child. So we mark it as visited. Okay, so we know that this last node that we visited that does not have a child any longer now. So we start backtracking and we start labeling nodes that we've backtracked as follows. So here, let's go with something more different. So here, backtrack. This one, no more children, backtrack. This one, this node up here has a child. So we go and expand it out as follows here. Okay. And we know that this node has a child, but it's already been visited now. So we begin backtracking here again. Backtrack. This one has no longer any children. Backtrack. S, the start node where we came from, has children. So we look at the next child. This one. This node has a child. This node doesn't have a child anymore. So we mark it as visited. This node still has a child that we haven't visited now. So we mark it as follows. This node is a sync, has no children here. So mark it as visited. Go back up. This node still has a child. Okay. So you mark it as visited here. Okay. And this node, we know that it essentially no longer has any children because it's a sync. Mark it here. This one, go back up to its parent, mark it here. And we know that S still has an out edge now, but we know that we've already visited that out edge. So we make sure that, okay, it's already marked as visited. So we close it up. So this is what DFS does. We track state, we look at identifications of whether nodes have been visited or not, and we keep backtracking. So I'll work you guys through another demo of DFS to give you guys a better understanding of what it does. So here, let me know if you guys have any questions lang. Okay, so this is some graph. Let's say this is node A, B, C, D, E, F, G. Let's make this bigger. A, B, C, D, E, A, C, D, E, F, G, H, I, J, K, and L. Okay, so let's start at this node here, A. And let's begin our DFS procedures now. So we know that A has children B, E, and C. Let's start with node B because we're going DFS now. Normally, you can just start at some arbitrary one. I usually like going left first. It really doesn't matter. Let's go here, B. Okay, so B still has children. We can expand. So let's expand D. It has children F and E, no, but I'm expanding D here. D has a child I. I has a child K and L. Let's expand K. K does not have any children, so let's mark this as visited and closed. No, so we go back up into I. I still has a child. Let's mark it visited here. We know that I has no children. And it's a sink. It's a dead end node. So mark it visited here. I no longer has any children. So here, mark it out as visited. So go back up D. D no longer has any children. So you mark it as visited. Go back up B. Does B have any children left? Yes. So we expand these children. F here has a child D. D is essentially already been visited now, so we don't need to keep track of that anymore. So we know that F is a dead end. So F here is marked na, and we go back up to B. B still has a child that we haven't visited, so we expand that E. And expanding E, E has a child J here. And now following the same algorithm, no, we essentially know that J is a sink. Close it, go back up into E. E has no longer any children. Close it. C, go back into B. Does B have any children left? Wala na. So we mark it as follows. And we go back to A. Okay. A still has children. A has a child E, but we know that E has already been visited. So we don't need to track that anymore. C is still an open child here. Okay. So we expand C into G. G is no longer at any, does not have any children anymore. So we mark that here. C is still open. C still has a child. Okay. So we mark that here. H has a child here. Going back. So we mark that here. And we know that, okay, A's children has already all been visited now. And this is where it can get tricky. A's children has already all been visited. So we backtrack here. Backtrack into H. H has no longer any children. C has no longer any children here. And given that we know that A doesn't have any more children, we already close it as follows. No? So this is DFS. It's, you'll notice that it's very algorithmic, no? So it's just gonna be basically a bunch of if statements where you loop through the graph. While the node has a child, you expand it. If the node no longer has a child that you visited, you backtrack, you go back up. So there are multiple ways of implementing this programmatically. I'll leave that to your imagination. You can use libraries for all I care. I encourage that actually. But this is essentially how DFS works now, and it's super useful for identifying, sorry, whether your graph is connected. It's useful for identifying connected components in a graph. And what connected components in a graph are now is essentially something like this. Going back to this visualization, you see that here are many subgraphs. No, you have nodes that are, you have graphs that are 2 nodes in size. You have graphs that are 3 nodes in size. Some graphs have maybe 7 nodes in them. No, so these are nodes. These are networks that vary in size, and you see that they all have the same color as long as they're connected to each other. These are called your connected components. What connected components denote, at least in a social network, no, are that these communities exist in social space. So for example, um, you guys will have very specific communities with your social media platforms. You will have your friends groups, you will have your family groups, you will have your high school friend groups, you will have your professional work friends. No, so these will all be separate and individual connected components that won't all be fully connected. No, so algorithms like DFS, depth first search, um, will be super useful in identifying these communities, these connected components. So going back to notability, here. Okay. We now move on to BFS. Which is bread first search. So difference is it's well depth first search is going deeper. Sorry, it keeps pausing. I don't know why. Depth first search goes deeper. Breadth first search goes broader. No, and it's useful because we can implement a few data structures that we might be familiar with in implementing your basic DFS algorithm. No, so BFS, similar to DFS, runs with a time complexity of O that is proportional to the number of vertices and edges that you have. BFS is known for being efficient at finding the shortest path, usually for weighted graphs. No, sorry, for unweighted graphs. And let's work through a really quick demo for BFS. Okay. Ito na lang para visually. Okay, so this is a graph that I tried really hard not to make a binary tree. Okay, so let's start labeling these edges now. Sorry, these nodes. Let's call this A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay. So when we work with BFS, we start at some arbitrary node first, and then we begin exploring the neighbor nodes first now before moving on to the next level neighbors of the graph. And we can keep track of the state by working with a sort of queue data structure. So a queue is a first in first out data structure. A queue way so that you don't misspell it is a FIFO data structure, no? Think of it as literally falling in line where it's first come, first served. You whatever is first processed, that is what we know is next to be served. No? So let's go. Let's start with an analogy, an example. Let's start with A here. So we have, let's say, our queue here. Let's put in A here, and then we know that A has children B, C, and D. So we add them into the queue, B, C, and D. Okay. Now, once we've exhausted all of A's children, once we know that, okay, A has these children, we can DQ that and start processing another level of our data structure graph, of our graph now. So here, we now have B, and we put in all of B's children into the queue now. So what do we have here for B? Sorry, where is that? So we have E and F. B has no longer any, sorry, there is no edge here. Should be edge there. Okay. Yeah, so E and F, so we add that here and F. Okay. So now that we know that B has no longer any children, we pop it out. Okay. And now we start at the next node that is in our queue, and that is C. So given here our queue, we've processed A and B. The next node to process in our queue is C. Okay, so here we have C. C has no children. It's a sync. So it's at the end. We dequeue that. The next node that we look at in our queue is D. So we look at D now. We know that D has these children G and N. So now we add that into the queue. Okay. So I'll move this down so that it's easier to work with here. Okay. So G and N. Okay. Once we've exhausted node D and its children and now, we go into the next essentially layer of our data structure of our graph. Now we dequeue D, and the next node to process in our queue would be node E. No, so here we have node E. This is what we are currently looking at now. We know that node E has a child J. So we have here J, and that's it. No, E has no other further children, so we can dequeue that. What's next in our list is F. F has no children, so we can mark that as visited here. F has no children, so we scratch that out. Next node to process is node G. Okay, so once at node G, mark that as follows. Node G has one child, K. So we add that into our queue. Okay. So we know that node G has no longer any children, ano? So we scratch that out here. And we go to node N, the next node in our queue. Here. And then we look at, okay, node N has I as a child as follows. So we know that, okay, N has no longer any children. You can scratch that out. Do the same thing again. J here has a child E, but E has already been visited. So we can scratch that out here. K, look at K here. K has two children. So I think I missed putting an I here. Sorry, there should be an I. N-I. There should be an I here. Sorry, what? K. Oh, come on, I lost track. Wait, give me 1 sec to figure this out. KJ. Pagpasok natin ng N. I. Okay, sorry. Yeah, there should be an I here. Okay. That was already scratched out. Okay. I'll just walk you guys through another demo later to make sure that you guys got stuff here. Okay. So K, we're looking at K now. We know that K has node expansions available. So we then go into I and M. We add them in here. Sorry, L and M here. So we know that K has no children. Scratch that out. And we look at L here. L has no children. Scratch that out. M, do the same thing. M has no children. Scratch that out. So this is essentially how your breadth first search works. We sort of process our network on a layer by layer method. No? Some other folks call it uh, um, some sort of level order traversal. Um, it's essentially a way to process the network on a layer by layer process now. Some other people call it layer order traversal as well. So it's usually useful for finding the shortest path now because we're able to expand nodes and find the best path instead of just hitting a DFS sort of approach to things. So let's work with a different demo of BFS so that it's a bit clear. If you guys have any questions, no, let me know lang. Okay, let's call these nodes 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and let's have a queue here. Okay, so let's start at node 1 here. Oops. Start at node 1 here. We know that node 1 is in the queue, no? And we expand node 1. So the expansion step, we find 4, 2, and 3. So we now add these here. Sorry. 4, 2, and 3. Okay. So node 1 doesn't have any more children that we can identify or expand. No? So we dequeue it as follows. So the dequeue step usually happens once there are no longer nodes to expand for the target node that you're looking at. So scratch 1 out. So that's essentially dequeuing it. Okay, so now we have 4, 2, and 3. So 4 is now what we're going to be looking at here. 4 essentially has no children, ano? So we know that 4 is done. We dequeue that. 2 is now what we're looking at. And we know that 2 has, well, 2 children, 8 and 5. So we add that into our queue as follows. Okay. So once we know that 2 has no longer any children to look at or to expand, once we've added them into the queue, we can scratch 2 out and dequeue that. And now the next node that we expand, the next node that we look at is the next one in our queue. So that will be 3. Okay. So we now look at node 3 here. And given that we're at node 3, we know that node 3 has 2 children. Let's expand these into 6 and 7. So 6 and 7 here. Okay. So node 3 no longer has any children. Let's dequeue that as follows. Okay. And then now the next node to look at will be node 8. So node 8 has no children. DQ. Node 5 has no children. DQ. Node 6 has a child, but we've already visited it, no? So we don't need to expand any further. It's in the queue already. So DQ. Node 7 has no children. Visit that. We DQ that. So that's essentially one of the ways to traverse a graph. This is breadth first search. It's a bit more involved than straight up DFS now. But I like breadth first search because it's more efficient when we try to look for the shortest paths for things. And you can really just implement it easily using a queue data structure. So that's it for the quick intro into graph theory and graph traversal that we have for today. The next lesson, async lesson, will be uploading, will be a lesson on heuristic search. It'll be all about A-star search, and we'll be using lessons and topics discussed in today's sync session to further the idea of a heuristic-based search algorithm that uses weighted directed graphs. If there are no more questions, guys, Thank you as always. Let me know if you have any feedback or comments on how to improve this course further. You guys sure you good? Any questions, clarifications, comments while I'm here? Yeah, no worries for being late or anything. This is an optionally synchronous course naman. So as always, we'll be uploading the material to Canvas for those who want to catch up. So no questions, guys? You guys sure? Like graph theory is one of my favorite topics because it's basically math but very intuitive, and it's still a very open problem. No, it's graph traversal, graph theory is usually on the order of n squared. It's a very hard thing to optimize. So it's a really interesting space to study, especially with AI. So yeah, if no more questions, sige, I'll be ending the recording na.
Hey, sir, question on the project.
Yes, yes, go ahead.
There was a question in Discord regarding the project, whether the project needs to be original or is it an original implementation?
Okay, I'm looking for that entry now. Give me some time to look for it. The question is whether it has to be original. Tama ba? Yeah. You can like, for example, ano, come up with. It doesn't have to be super original. If you wanna define a game as, um, I don't know, Pac-Man, you can create your own Pac-Man like game. Just don't call it Pac-Man siguro. No? The mechanics doesn't have to be strictly original. You can come up with a game that you like. If you wanna I don't know, represent Breath of the Wild in an agent based system, now you can come up with that. UI, we don't need to implement a UI. No, printing via console will suffice. If you wanna do a UI, feel free to challenge yourselves and do so. I did that 8 years ago, 7 years ago, and I just shot myself in the foot because I was making an interface for a battleship game using weirdly Ruby on Rails. No, so think about how complex that would be. But yeah, as to whether it has to be original, not necessarily. UI not needed because yun nga, not everyone here in this course has the prerequisites for programming that an interface. So I hope that answers your question.
Yes, sir. Thank you.
See anyone else? We good? Sige. If there are more questions na lang or if they need to be offline, let me know. Required to work in groups? Yes. Groups of 3. If you end up without having groups by the end of the week, let us know and we'll try to figure out. Maybe there probably will be a bunch of you without groups, so baka ipag-grupo na lang namin kayo kung ganun. So I'll be ending